All right, so this is week 2, and as promised, we're going to start talking about how to actually make sound in SuperCollider this week. So last week, as I mentioned, SuperCollider is actually multiple programs kind of bundled into one. There's sclang, which is the programming language part of it, and then there's ScSynth, which is what's called the audio server, and that's a separate program which communicates with sclang to make all the sound. And when you first launch SuperCollider, the interpreter, which is the program that reads and parses your code, that program is launched, so that's active. You can see in the bottom here, but the audio server is offline, as you can see by little white zeros in the bottom right. So let's boot the server, and the most typical way to do that is with code. You can just say s.boot and run that code. And there's other ways to boot the server. You can click on these numbers, and there's an option to boot or reboot the server here. In the server dropdown, you can boot or reboot the server here as well. Actually, before I go any further, I just do want to quickly make sure that we have some sound getting recorded. And that looks good to me. Okay. So just pretend you never saw that. One thing you might ask yourself is, what is S? We talked about local variables and environment variables. One thing I didn't mention last week is that the single lowercase variables without a tilde, also that b is left over from something earlier, so you can just we'll just set that equal to nil, just for right. So all these things are just nothing right now, but we can set them equal to stuff, and they behave. Sorry. D plus 3, they behave in the same way as the environment variables. And we didn't give S a value, but it's, if we evaluate it, it returns localhost, which is the name of the instance of scSynth that runs on your computer. And it's stored in S as a convenience, sort of behind the scenes when you boot SuperCollider. And because there's lots of different reasons that we want to talk to the audio server, and just having it in a single character variable is very helpful. So that's why s.boot works. So we've got the server booted now, and we're ready to make some sound, as we just did a second ago with a little bit of pink noise. So pink noise and many other classes are examples of a family of classes called UGens. So the abstract parent class of all UGens is this UGen class, which by itself doesn't really do anything, but it defines all of the common functionality that is inherited by various UGens. In the, I think there is a browse UGens file. Or maybe I think it's called tour of UGens. Tour of UGens, yeah. So this is a help document which you can explore just to get a sense of the different UGens and how they're categorized. And on page 37, I think it is, of the textbook, I have a small table of what I've kind of arbitrarily isolated and selected as commonly used UGens. So we're just talking about things like oscillators, noise generators, filters, objects that read sampled audio that's stored in a buffer, and lots more. Delay lines, granulators, just lots of different stuff. So UGens are the basic building block of synthesis algorithms. Like when you're working at a modular synthesizer, you have various modules available to you, and you'll interconnect them to create more complex sounds. And the concept is pretty much exactly the same here, except we have lots and lots of modules, and we call them UGens, and we're not limited by physical hardware and stuff like that. So let's actually just take a look at pink noise, since we've already played it. So we can help file it, and gives a brief description. It's just a unit generator that generates pink noise. Not much more complex than that. The class method that creates an instance of a UGen is one of these rate methods, AR or KR, Some also accept IR. So they stand for audio rate, control rate, and IR stands for initialization rate. IR is pretty rare. Not all UGens understand it. I mean, different UGens will understand different rates, but for the most part, AR and KR are pretty common. AR means audio rate, KR means control rate. So a UGen running at the audio rate will output a number of samples per second equal to the sampling rate of your system. And right now, for me, that happens to be 48,000. So it's going to be, as high of a resolution of a UGen as we can possibly create. Full resolution, it's the type of UGen you have to use if you actually want to play its output to your speakers. It has to be an audio rate unit generator. Control rate unit generators run at an integer division of the sampling rate. And by default, that's 64 samples per control block. So they have 1/64th the resolution of an audio rate waveform. So the benefit of KR is that it's computationally less expensive, but it's not a good choice if you want a unit generator that has a very high frequency or a lot of quick movement or something which needs a lot of resolution to represent. So like slow-moving envelopes, for example, it's a great opportunity to use KR. You can use AR for everything, but it's just not very efficient. And so you usually want to be mindful of what exactly these UGens are meant to be doing and use a control rate oscillator when appropriate. OK, so in addition to these rates, every UGen will take some number of arguments or parameters. These are values which determine the output of the UGen. And in this case, we have something called mul and add. And mul is a scalar value that will be multiplied by every output sample, and add is a value that will be added to every output sample. So in a very simple sense, mul is basically just an amplitude parameter. And so a value of 0 means every sample is multiplied by 0 and we have a perfectly flat signal and silence. And a value of 1 will not modify these values at all, right? Add equates to DC offset, so you'd be actually biasing the signal up or down. Generally not something you want to do when playing to your speakers. OK, so we might think, great, let's play some pink noise. We didn't get anything. It's not working, right? Where's our pink noise? And so UGens by themselves define synthesis processes, but in order to actually hear them and play them to your speakers, we need to enclose them in a function to define what's called a UGen graph function, and then send it the play message. And so this is a construction called function.play. Well, I don't know if it's officially called that, but that's what I call it. So we'll enclose this in curly braces, and I'm going to dial this back so it's not too loud. And here we have a function which contains a unit generator, and we are playing it. And before I run this, I'm going to talk about how to stop sound, because once we play it, there's going to be no obvious way to stop it other than just, I don't know, maybe quitting the server, quitting SuperCollider, or just covering your ears or something. So there is a keyboard shortcut, which is Command period on Mac OS and Control period on Windows and Linux. So this is the most important keyboard shortcut to memorize. I often will code with one hand over Shift Return and the other one over Command period, just out of habit. So we'll just run this, and then I'll let it run for a couple seconds, and then we'll Command period. And we have nothing. Why? Let's see if I can do this. Oops, something's happening here. Pink noise. Oh, you know why? We're running at the control rate. OK, so I've already managed to mess this up. What happened there is we played that function, and it generated a control rate pink noise. And that's just simply not something which can be written to our hardware outputs. So let's change it to AR, and now it should work. and control period to stop that. Okay, sorry about that. So one thing you might notice is that it's just one channel coming out of the left speaker and not the right speaker. So we'll get to multi-channel signals a little bit later, but for now, I just want to remind you all of this exclamation point shortcut here, which is an abbreviation for the dupe method, for.dupe3 or for exclamation point 3 means create an array of this many things, and this is the thing to fill it with. So what happens here, if we just run this code, is we get two pink noises in an array. And when we try to play an array of signals, SuperCollider will automatically assign those signals to adjacent hardware outputs. So in the case of a basic stereo setup, left and the right. So it's just going to copy these into both channels. And all UGens have their own set of parameters that they accept. And so when you first open an enclosure of parentheses on a unit generator, you'll see a little pop-up, and it tells you freak, phase, mul, and add. You can also drop into the help file with Command D and just take a quick look if there's a sort of description of these parameters. But in the case of a sine wave, it's pretty self-explanatory. We have the frequency, we have a phase offset, and then again we have mul and add. Mul and add are pretty ubiquitous throughout the entire family of UGens because it's just nice to have a value which will scale and shift the UGen as needed. So we can go in here and say, let's make a nice mellow 200 hertz sine wave with an initial phase of 0. We'll set the mul to be 0.1 and the add, getting ahead of myself here, to be 0. And we'll scale this. Oh, we don't have to scale this down. Or we'll exclamation point 2, so it comes out of both speakers, right? Right, very nice. There's a couple different syntax styles you can use for these arguments. If you were to just sort of look at this, it just kind of looks like a bunch of numbers, right? It's really not clear at a glance what these numbers mean. So we can do argument keywords like this, as we saw something similar with functions last week. This is longer but more descriptive, so it's really just a matter of taste and personal preference. The nice thing about the keywords is that you can, sort of just provide only the ones that you're interested in dealing with. Like we can just use the default phase value, we can use the default add, and this is fine as well. So just it's important to keep in mind that all UGens are unique, and so something you should never do, especially if you're not using the argument keywords. Just if I were to just say something like this, thinking I'm providing frequency and mul, this value is going to get interpreted as the phase, and the mul is going to fall back on its default value of 1, and so this is actually going to be a fairly loud sine wave. So we won't run this. So we can do something like this. In the case of using some keywords but not all, the ones at the beginning will get interpreted in order. So 200 will be the frequency, and then SuperCollider will skip over phase and use mul here. So I think there is a companion code in chapter 2 that kind of goes through these little nuances just in more detail here. So let's you never want to do something like this. Just think, okay, let's just swap this sine wave for pink noise. What's going to happen here? Who knows, I guess, right? We're providing mul here, but 200 is also the first argument of pink noise. So we're not only is it conflicting, but it's kind of dangerous because we don't want to just plug 200 in for. Let's just go ahead and delete this, just to make sure. Make sure we don't actually run it. Yeah. Okay. So let's see. We have sine waves. It's just 200. 0.1, exclamation 2, wait for seeing this one. And pretty much all of the oscillators, like we have a sawtooth, right, they all start with frequency. This one does not have a phase value, so this works just as fine. And we also have pulse waves, triangle waves. In addition to pink noise, we also have white noise, brown noise, various other noises. If you go into the help browser, you can go to Browse. You can scroll down to UGens, and there's all these categories of different types of UGens. And if we go to generators, we can then go to deterministic, and this gives us access to a lot of the deterministic UGens. So things like, oscillators and so on and so forth. And then we can go back to stochastic, and that'll give us the various noises. So there's a lot of these to play around with and try out sort of on your own. As you go through chapter 2, you'll probably get a better sense of what's available. But for now, we're just going to kind of focus on these generators. Okay. Yes, please.
Are the UGens written in SuperCollider as well, like in a way where we could see sort of the source code, or how? Or are they written more low level?
The UGens are written in more low level. Yeah, those I think are written in C or C++ or something. And so I think if you go on GitHub and you look at the SuperCollider project as a whole, I think it's possible to see the UGen code there. But from the IDE, I don't think we have immediate access to the source code for the actual UGens themselves. Yeah. Okay. Let's build a sort of more interesting and complex UGen function. Let's just do something very simple and do like vibrato on a sine wave. Right? How do we just, in plain English, how do we deal with vibrato on an oscillator? Regardless of soft, just walk me through it. Right? What is vibrato? Sure, or frequency, right? We're causing the frequency of an oscillator to fluctuate over time. And so how, in sort of more technically, how do we implement that?
We modulate the oscillator by another LFO.
Very good. We modulate the frequency of one oscillator with an LFO. So let's do that. Let's even go ahead and define some variables just to write our code more neatly. So we'll need our signal and low frequency oscillator. So we're just declaring some containers so that we don't have to do this all on one line. And so let's our signal is going to be a sine wave. We'll give it a 200 hertz once again. We'll make it stereo here on the end. So if we just play this now, we're going to get our 200 hertz wave here. So what might we use for our LFO here? What do you think? Sure. Audio rate or control rate? Control rate seems reasonable. If we're doing vibrato, that's usually 6 or 7 hertz or something, and so that's pretty low, and a control rate oscillator will do a perfectly good job of that. And so here's where we get into a discussion of the output range, the numerical output ranges of these unit generators. And by default, almost every UGen will have an output range that is either bipolar between negative and positive 1, or unipolar between 0 and 1. And a sine wave is bipolar, which means it's going to have an output range that goes between negative 1 and positive 1, in this case 6 times per second. So maybe we can use that as is. For example, if we were to add this LFO to the frequency of this sine wave that we're listening to, well, that means the frequency of the sine wave we're listening to is going to fluctuate between 199 and 201 hertz 6 times per second. I think that's going to be a little small for us to hear. Let's hear what it sounds like. Yeah, it's like on the threshold of perception. Maybe if what you're listening for, you can sort of hear a little bit of a variation in the tone, but it's almost not enough to notice. So if we want a vibrato with more depth, what would we do? How would we change this function? Multiply LFO. What do you think is a good value here?
3 or 7.
Let's try 3. Okay, so now what is going to be the output range of this LFO?
197 and 203.
Well, that's going to be the resulting frequency.
Yeah.
Right. So but this will range from negative to positive 3.
Yeah.
So another thing to point out here is that what we have is a unit generator multiplied by a number. And as we saw last time, when we multiply, like number by number, we know how to do that. Multiplying an array by a number, the default behavior is to apply that multiplication to every item in the array. And here, a UGen is really basically just a number that is constantly changing, or an infinite sequence of numbers. I mean, that's all UGens really are. They're just signal calculators. And so SignOsc is going to be spitting out floats between -1 and +1 for as long as we let it run. And this operation is defined as applying this multiplication to every sample in that unit generator. So it's simply going to upscale the LFO. And just to point out, we could just as easily do this, and that's the exact same operation. So either is fine. Let's see what it sounds like. Yeah, and that's definitely noticeable. We can make it much higher. Right. And you know, if we start increasing this value, we'll start getting into frequency modulation synthesis territory. So let's just go ahead and do that. We'll keep it control rate for now, but I'm gonna, let's see, increase this frequency a little bit, make it a little quieter, and so now it'll sound like this. Right. And I'll make this 200. We got kind of a police siren thing happening here. And you know what? Let's introduce another fun UGen. So mouse X will track the horizontal position of the mouse on the screen, and it will map that position onto this range from 1 at the left to 400 on the right. And this value is a warping parameter. 1 means it will map linearly. Sorry, 0 means it will map linearly. 1 means it will map exponentially. And I'm pretty sure this is documented right in the help file. And while we're here, let's also poll. Poll is a debugging method. It will print in the post window the value of the UGen at a default rate of what I think is 10 times per second. So it's not going to print every sample value. That's a pretty, even for KR UGens, that's a pretty daunting task. It's not really realistic to print that many values per second in the post window. It's just too much. So let's now do this. Here we go. Oh, I forgot to plug it in. OK, we want to do this, right? Actually use the mouse values for the LFO rate. Let's compare that kind of crunchy sound to using an audio rate modulator instead. And that's a pretty clean and clinical demonstration of why audio rate and control rate sort of matters, because as soon as the up and down behavior of a control rate UGen gets too fast, it just doesn't have enough samples to represent that shape, and so aliasing starts occurring, and we just get this kind of the fold over and kind of junk data, and so we just get this kind of crunchier sound. Not really right or wrong, it just is what it is, and maybe you're in a crunchy mood some days, and that's totally fine. But just to, at low frequencies, AR and KR really doesn't matter too much. There's just no sort of noticeable difference. But over here, yeah, quite a noticeable difference. So yeah, definitely keep that in mind. You will probably remember from last week that when we define a normal function just with basic programming stuff in it, what is returned on evaluation is the value of the last expression. And something similar is happening here as well. When we play a function that contains a interconnected cluster of UGens, the signal that gets sent to our speakers is the last expression here. So if we were to just say, you know what, let's actually add some pink noise at a low amplitude over here, then all of a sudden, that's what we hear. We can also just put a 0 at the end. And this is a way of just muting the function. And you can see, as evidenced by the numbers in the post window, that the other stuff in the function is still running and consuming processing power. It's just that we've done all this, but then we're saying, oh, and play silence. So I mean, this is actually kind of useful for a variety of reasons. Like if you're just you want to see some numbers, but you're not sure if they're safe, and you just want to make sure you don't play them, you can always put a 0 at the end, and that's sort of a convenient thing to do. Okay. So I've been doing command period this whole time, and that's fine, but it's it's if we have multiple sound functions running, like let's have this one which has a base frequency of 800, and this one which has a base frequency of, let's say, 1500. So they sound different. And I'll bring this up to 100. Right? This one sounds like this, and this one sounds like this. So if I play them both, command period is indiscriminate, and it's just going to wipe them all away. So it's a good idea to give these names. So you want to, when you're playing a function, you want to store the result of the function.play expression in some variable. And so that'll be, we can run this and this, and then we can say x.free and y.free. Right? So free is, it's a similar hard stop, but it is selective. You can actually talk to a specific sound process, assuming you've given it a name, and you can terminate it, one at a time. But there's a convenience method for this function.play trick, and we can also say release instead of free with a value in parentheses. So, oops, didn't mean to run that again. Yeah. So there is a lot of stuff going on in the background. I mean, this function.play business is really just a handy shortcut. It's sort of like the quickest and dirtiest way to make sound. Later on in chapter 2, we won't get there today, but we'll talk about synth and synth def, which is the more sort of official way of defining and playing synthesis algorithms. So, but let's try to make something a little bit different. Let's do like some ocean noise with some brown noise and an LFO for modulating the amplitude. So I'll just do this, and we'll keep the tilde x, that's fine. Don't need this. We'll come back to this. And brown noise, we'll have a nice low amplitude here. And put that there. So this will be, let's do, I guess we'll just do another sine wave. A nice low frequency, maybe a cycle every 2 seconds. And the default range of sine osc, as I've said, is -1 to +1. So it wouldn't be irresponsible to just multiply this by this, but it's well, let's just see what it sounds like. This should be okay. Let's just look at the values of the LFO. They're going up to +1, up to -1. And so if I want these to go from 0 to 1, how do we do that? Well, one option, okay, we know the default range is -1 to +1. So we could multiply by 0.5, resulting in a range from negative to +0.5, and then add 0.5, which would bump it up by 0.5. So we could do that. Let's go ahead and do that. Something like this. And now we have a sine wave controlling the amplitude, which goes from 0 to 1 back to 0 over the course of 2 seconds. All right. We could also, do mul 0.5, add 0.5, and this is fine as well. Oops, what am I doing here? Oh, right. I got confused for a second. We need also the frequency, which was also 0.5. But I like to start here because doing it with sort of basic multiplication and addition is the foundation of every scaling operation. But it's not a nice way to think about it. For example, if we wanted to, make a sine wave range from 800 to 1700 or something like that, no one wants to be burdened with having to, reverse engineer the mental gymnastics of figuring out the exact math, and no one should. It should be a crime. So there's a better option, which is one of several range mapping methods. So just as an example, we can say range 0, 1. And what this will do is take a sine wave with the default output range, and it will figure out the math so that its output range becomes 0 to 1. And this is a linear mapping method. So it's just going to be another proportionally accurate sine wave from 0 to 1. So that's fine. We can also, map it so that the peak is a little bit quieter. A more quiet day at the beach. Let's see. Let's do. I'm going to make this a triangle wave. Right? So same frequency, and we'll go 0 to 1, and we'll hear what this sounds like. Okay, so nice, perfectly linear ramps. And if we do exp range, keeping in mind that again we can't cross or include 0 when doing exponential mapping, so we will have to change this a little bit. But listen to the difference here. Okay. So what it's done is taken this triangle wave and not only mapped it to this new range, but also done so with an exponential skew, so that the values get sort of pushed closer to the bottom end of the range. How's everybody feeling about this? I know I'm a little all over the map sometimes with introducing, because everything's kind of interconnected. But are there anything you see on the screen here which raises a question? Is like, wait a minute, what's that doing there? Or, yes?
Just curious, for the ranges, can it handle, say, negative ranges, like from 0 to -1 instead of?
Yes.
Well,
X range can't handle a range that crosses 0, but range can. So I'm trying to think of a good example here. Let's just do it with another frequency modulation example, because you can feed sine osc a negative frequency and it will just flip its polarity. So we'll have a sine wave. Let's give it just 1 hertz, and the range will be -200 to +300. Right? You can just pull this really quick. Right? Right? So you can see the values.
I think what I was thinking was, if the range started with a higher number, like instead going from 300 to -200, does it?
Oh, like if you were to provide these in the opposite order?
Yeah.
Yes, I think the result is what you would expect, and it will just the maxima will become minima and vice versa. Yeah. Why don't we put that to the test? Just let's do a pulse wave. No, actually, I'm not sure pulse is going to respond to negative frequencies in a pleasant way, so we'll do it this way. Looks good. And we do it this way. Switch these. Yeah, so you can see that just basically the modulator got flipped upside down, more or less. So yeah, it's pretty intuitive in that sense. All right, let's talk about real-time control. So all of these functions, we've been playing it, and they just kind of run autonomously, and we can't really interact with them other than just stopping them or releasing them. So let's make it even simpler, and we'll play let's do a filtered sawtooth wave. We'll say 50 hertz, scale down a bit, and then we're going to pass this through a low-pass filter with a cutoff frequency of 1,000. Right. So sounds like this. Right. And let's say we want to be able to change the cutoff frequency, sort of with. We could plug an LFO in here, and we sort of already know how to do that. But let's say we actually want to, change this value manually, on the fly. So the way we do that is we define an argument. And we've seen this. I think we've seen this already. Where we with iteration and with just functions, we want to be able to pass a value into this function. And what's actually happening here is that when we play a function and it's got arguments defined, it creates behind the scenes an instance of a class called control, which is just a UGen, which allows external data to be passed into the synthesis function as it's running. So we definitely want to give this a default value. I don't know what happens if you set the cutoff frequency to nil. Maybe it's got a failsafe in here, but it just seems like kind of a dangerous thing to do. So we provided this argument. It's 1,000, so we get the exact same thing here. And now that we have this argument, we can use a set message. So basically, we can talk to the synthesis process while it's running, and we provide two things: a symbol of the argument that we've declared, and then the new value. Right, then we can just fade it out at our leisure. Right. So set messages are pretty handy. And I don't think this is in chapter 2. Maybe it is. But there's a unit generator called lag, which is basically, essentially, it's a low-pass filter. But more practically speaking, what it does is when its value changes, it will interpolate from its current value to the new value over some amount of time. And I think this one is always exponential. There are a few other classes. Varlag is one where you can actually shape the interpolation to be linear or exponential or whatever. But lag, so what we could do is say cutoff equals lag.kr cutoff, and then we'll say 2 seconds. And so now, when we set, it takes 2 seconds. Sort of jumps. It sort of quickly at first, then levels off. So just if you're looking for a sort of basic interpolation function of these set messages, so they're not always instantaneous, lag is useful. And there's a sort of a convenience method for lag. So you don't have to do all this business here. You can just say .lag2 at the end. And this is just a convenience for wrapping the receiver in a lag UGen. Right, just to confirm this still works. Yeah. Alternate syntaxes for arguments. Let's go and grab this down here. And we'll forget about the lag here for a second. You might see, I think in the book I favor the pipe syntax. We've seen this already, I think. Yeah. But there's yet another one which I've kind of adopted more regularly, which I don't think is in the book, but there's it's to not bother with the arguments at all, and instead down here you provide a symbol followed by KR and then the default value you want to give it. And one thing I really like about this is that it basically color codes your arguments. So you can very quickly look at your UGen function and see where the arguments are. You can see what their default values are and their rates kind of all in one. And so, same thing applies here. We can run this function, and so all works the same way. I tend to advocate this style now, but it's you can do the actual ARG, you can do the pipes, and you can just put them in line with this symbol rate default value syntax. And yes.
Does the named control style have a lag built in as well?
I think it does. It's actually the second argument. Yeah, so you can put a lag right into this enclosure, which is pretty nice. So. Yeah, thanks. Yeah, it's good to point that out. Okay. Let's see. There's more stuff to talk about. I think this is sort of a 2-week lecture. It's a big chapter, chapter 2. Any other questions right now? Yes.
So the inning, is that just like the first declaration? If you want to use it more in the function, does the syntax change across?
Oh yeah, if you want to use cutoff multiple times, like have another filter with the same cutoff. Yeah, the style I recommend for that is okay. So the problem with that, if let's just pass it through another filter with basically like just stack 2 filters in series, whatever. This I think will be fine. But if you have a different value, it's going to complain. It's like, wait a minute, I don't know what to give this. So what I've seen people do and what I like to do is you declare a variable and set it equal to an instance of control, like this. And then throughout here, you just say cutoff. I mean, these have to have the same, it's the same thing. You can't give it 2 different values. But that way, we just, up front, we declare a container, which is a reference to this singular control. So we just define it up here, with lags if we want, and then we can just deploy it multiple times. A better example might be like if you have multiple oscillators and you want them to all have the same frequency or something like that. So this is a pretty clever trick for that sort of thing. All right. So everyone sort of understands sort of math with UGens, and that when you do a mathematical operation, it's going to apply to all the samples. You can also add 2 UGens, and that's just linear summation, right? So if you add a sine wave with pink noise, you'll just hear both of those at the same time. So once we play sig, it is actually this sine wave, which has then been added. So it takes the corresponding samples of each one. I see a lot of nodding, so I'm not gonna spend any more time on this. And range mapping. The last thing I want to talk about range mapping before we leave that topic is something you should never do is provide mul and add values in the parentheses followed by a range mapping method, because you're going to get a double dose of range mapping. All these range methods, range, xrange, and the others, they expect to be applied to a receiver, which is a UGen outputting its default range. And so really behind the scenes, what these range methods do is apply a mul add operation. And if you do that in the arguments for the UGen and then follow it up with another mapping, you're going to get some different range that you're not expecting. And this can be really dangerous depending on context. So however you want to map, the ranges of your UGen outputs, do mul add yourself, or I think much more preferable is to use one of these range mapping methods where you can explicitly specify the min and max, but don't do both at the same time, because you'll get something weird. So let's spend the rest of our time here talking about envelopes. The main UGen for envelopes is called envgen. And let's just take a look at how it works. So we'll make a UGen function, give it a name, and we'll declare some containers for the signal, and then we're going to just do a basic amplitude envelope. So the signal will be let's do a pulse wave. Let's say 100, something like this. It's so loud. Here we go. Nice pulse wave. We'll do an envelope. So we're going to use envgen.kr. And the basic things that an envelope needs is an instance of env for the actual envelope. So env is a different class. It's not a unit generator. It's just a language side object that represents an arbitrary time domain function that can serve as an envelope. And there are lots and lots and lots of different methods for env. We can just do env.new, which is kind of the most flexible. It's just a choose your own adventure envelope. But then there are things like env.adsr, env.triangle, we can even look at some of these just separately outside of this context here. We'll say env.perk.plot, and there's a percussive envelope shape, env.triangle, maybe it's try. Did I misspell it? Yeah, I think I just misspelled it. Did I misspell it? Okay, sorry. Okay, yeah, triangle, env.sign. The ADSR also plots. It looks a little funny because the sustain level is just represented as a single point, but in this envelope, this is the value at which the envelope would sustain for as long as we let it. But env.new is probably the one that's best to kind of, get familiar with. And env.new takes 3 arrays and some other things, but at minimum we need an array containing the actual points along the breakpoint function. So we'll say 0 to 1, back to 0. An array of durations, so we'll do a 1-second attack and then a 3-second release. And then an array of curvatures for the segments that connect the points. 0 is linear, so here we have a sort of skewed triangle shape, which goes from 0 to 1 over 1 second, 1 to 0 over 3 seconds, and both segments are linear. If we change this to, let's say, a 3, it's going to bend that segment so that it changes slowly at first and then quickly towards the end. Negative values do the opposite, right? And so any float is valid here. Like, you can do some really extreme stuff with that curvature. This is a curvature of 30. And you can add more segments. It doesn't have to be just 3 points here. So let's copy this with the -3, plot it again just so we remember what it looks like. And then we'll copy this envelope and just plunk it down in here for the first argument. Right? And just use the keyword style. So the first is envelope. And let's just leave it at that. There's more that we should be doing, but if we want to control the amplitude, all we do is multiply it by the signal. So that'll sound like this. Let's do a little randomness here. And as I run this, if we look in the bottom right, you'll notice that the CPU usages are just gradually creeping up every time I run another one of these functions. And that is because when we generate a UGen that's making an envelope shape, as long as we let this function tilde(x) continue playing, the envelope doesn't actually ever finish. It starts at 0, it goes to 1, goes down to 0, and then after 4 seconds, it just hangs out at 0. And it's continuing to output 0, and those zeros are continuing to be multiplied by the signal. And, even though it's 0, it's, a sample is a sample, and so these UGen functions are continuing to exist. And so we can actually look at the node tree, and we see that we have all of these synthesis functions that are just lingering. So we'll command period on that just to wipe them away. So this introduces the concept of done actions. It's probably in the NFGen help file. If we go down to the last argument here. A done action is a flag specified using a done UGen or just an integer, which tells a UGen function what to do with itself when a finite UGen is finished. Let's see if we can, here's a list of the different done actions. The default for most cases is 0. So if you don't specify a done action, it falls back on 0, which says do nothing when the UGen is finished. So after 4 seconds, NVGen checks the done action, which is 0. It says, OK, do nothing. I'm just going to keep hanging out, producing zeros. And then there are others. Pause the UGen function, free the UGen function. There's a bunch of, more specific, complicated-looking ones. As I tell students every year, the only done actions I tend to use 99.9% of the time are 0 and 2. 0 does nothing. 2 frees the enclosing synth. So we can skip ahead to the done action and specify 2. Or you can do done.freeSelf. This class, done receiving the free self method just returns the number 2. So this is a more verbose way of, readable way of doing it. I'm in the habit of just doing 2. You can do whatever you like. And so now if we bring back that, let's close some of these, and let's bring back the node tree here, and we'll just tuck this over to the side. And what I'll do is I'll play this function again, and this time the envelope has done action 2. So 1 second up, 3 seconds down, and at the 4-second mark, NVGen checks the done action and says, oh, 2, okay, we better get out of here. And the whole, so basically this, it's like a process that automates the sending of a free message. Right? So it happens automatically, and so it's a great idea to put done action 2 inside UGens that are controlling the overall durational lifespan of that. Right? So for one-shot envelopes like this, great idea. And let's quickly take a look at a sustaining envelope. So let's do an ADSR envelope. So we take a couple of things here: an attack time, a decay time, a sustain level, and a release time. And you can also specify the peak level, but you can also just scale by a number, and that has the same effect. And curves for the segments. So let's just say 0.02 seconds up, 0.3 seconds down. We'll sustain at a level of 0.2, and then a 3-second release. Just going to plot this. So here's our attack, our decay. We sustain at this point here, and then go down. So the question is, how long do we sustain? And envelopes that are capable of sustaining will rely on their gate argument in order to determine how long to hold the sustain point and when to conclude the rest of the envelope. So the envelope will start and proceed and hold at the sustain level when the gate is positive. And when the gate is set to 0, that tells the envelope to move on from the sustain level and go to the end. And so if we just specify a hard 1 here, then we won't have any way of actually setting it to 0. So what do? We make an argument, right? Anytime we want to have real-time control over some parameter, we want to make an argument. So let's just say gate.kr, initially set it to 1. And now, when we play this function, the gate will initially be 1, and so we'll hear a 2-second attack, 3-second decay, and then it'll hold at 0.2. Keep in mind we're also scaling the pulse wave down, so it's maybe we'll bring this up a little bit. And I'll prepare the appropriate message to end the envelope. So it sounds like this. And we'll just hold here forever until we 0 the gate. The other companion code in Chapter 2 is called All About Envelopes. There's a lot of nuance. I honestly could probably fill an entire lecture with all the different features of env and envgen and the ways they can be used together. Also worth keeping in mind that you can just as easily use an envelope or an envgen to control some other parameter, like frequency or something like that. When you're synthesizing, percussion sounds like kick drums and such like that, it usually involves a sine wave that starts at a high frequency and then very rapidly exponentially decays down to a lower frequency. And I think there's a companion code at the end of chapter 3 on synthesizing percussion instruments, but we don't want to get too far ahead of ourselves. So my goal here is just to get everyone comfortable with building simple but interconnected combinations of UGens for basic modulation and envelope control. So if you're still feeling a little fuzzy on any of that, feel free to stick around and ask questions. I will upload the answers to last week's homework and make available the second homework, which will be basically more of this, debugging and building simple UGen functions that make sound. All right? Okay, thank you very much, and we'll pick up here next week.